Okay, so let's look at this question. So the question is, determine the rate law and the rate concentration for the reaction between, I guess, the first compound there, first ion, is ammonium, and the second one there would be called nitrite. So what is a rate law? A rate law is basically just an equation that tells you when you change the concentration of something, what does that do to the rate of the reaction? So as we've talked about in class, when you change concentration, that's going to affect the rate, but it's not always just like a one-to-one ratio. Sometimes you change the concentration and the rate will dramatically change. Other times you change the concentration and the rate might barely change or maybe won't even change at all really. So the way we figure out how the two go together is we write a rate law. So rate laws always look like this. Rate will equal the concentration of each reactant raised to some power that I'm going to call x and y. So really what we need to figure out is what x and y are. So the way you do that is you look for two experiments where only ammonium is changing, NH4. And when we find those two experiments, whatever happened to the rate must be due to the fact that the amount of ammonium is changing. So it looks like to me that's going to be experiment 1 and 2. So if you look at those experiments, the amount of ammonium changed, but the amount of nitrite stayed the same. So what was going on with the rate? Well, it increased, and the reason it increased was because the amount of ammonium was changing. So to figure out that x, that exponent there of x, we're going to set up a ratio. Now, a couple of things I pointed out in class. When you set up this ratio, always put big numbers on top of that ratio. Why? Because it makes your math the easiest. Now, the other thing that's going to help you out again is when you set up the ratio, make sure that when you put x, as I'll show you in a minute, x belongs on the concentration side. All right, so let's go over here and do our work. So I'm going to set up a ratio where I'm going to say the rate of experiment 1 and 2 compared to each other was changing because the concentration of NH4 was changing. All right, so again, on the concentration side, that's where the exponent is. Just like in the rate law, x goes with the concentration. Now, the other thing we have to do is figure out, well, when I set up this ratio, what goes on top? And if I look at these, the experiment 2 values are bigger than the experiment 1 values. Just go ahead and look at those concentrations. You can see concentration experiment 2 was bigger. So I'm going to put experiment 2 numbers on top, and that's going to be on both sides. And now we'll plug in and solve. So as far as that goes, the rate in experiment 2 was 18.7. Now you notice it says times 10 to the minus 7, but that would be on top and on bottom, so that's going to like cancel out, so we can kind of ignore that. So on the bottom goes experiment 1, and then on the right hand side goes the concentrations. So concentration for experiment 2 and the concentration for experiment 1. All right. So as far as that goes, now we've got a ratio, and we're just going to do our math and solve. So if I divide 18.7 divided by 10.8, I get 1.7 equals. And then if I divide 0.6 divided by 0.3, I get 3 to the x. So we got to figure out what x is. So what x is, sometimes you can figure out what it is in your head, but this one's going to be a little tough. So the way we need to do that is to solve for x. I'm going to first take the log of both sides. So you get the log of 1.7 equals, oh, and how did that work again in math class? If you take the log of this, what does that do? That brings the x up front, and then you get the log of 3. All right, so now if I actually type this into my calculator, the log of 1.7, I should say, is going to be 0.23, and the log of 3 is 0.477. All right, let me rewrite it up here, and we can finish this up. So this is what we got now. All right. So now what I need to do is solve for x. At this point, it shouldn't be too bad. You divide both sides by 0.477. The 0.477 will cancel out, and you get x equals, now I'm going to have to round a little bit. It's basically, it's not quite, but it's basically 0.5, or we'll call it a half. All right, so that means my exponent for x is a half. So we're going to put a half into our equation. All right, so that's x. So now we're going to have to go ahead and do the whole thing again and solve for y. We'll do that on another slide. Okay, so where are we at now? All right, so now we have that rate law. Rate equals K times the concentration of NH4 positive. And we figured out the exponent there was a half times the concentration of NO2 to the minus 1. And we still got to figure out what y is. So now we're going to have to figure out what y is. And the way we can do that is to find two experiments where y is changing. So it looks like to me those experiments are 3 and 4. So let's just double check. All right, so if you look in 3 and 4, right, in those two experiments, the amount of ammonium is the same number, but the amount of NO2 has gone up, and again, that changed the rate. So whatever happened to the rate, the reason why it changed is because the amount of NO2 changed. So we're going to go through the same process we did a minute ago. We're going to set up a ratio where we have rate on one side, and we're going to have concentrations on the other side. So the concentration that we're looking at right now is the concentration of NO2. Now again, a couple things to keep in mind so you don't make a mistake here, a silly mistake. Y is going to go in this equation. Which side does it go on? Well, just like in your rate law, it's going to go on the side where NO3 is. So it's the concentration raised to the y. Now the other thing we had to double check to make our math easier, we're going to put those values in, and to set up the ratio, always put the big numbers on top. So the big numbers are in experiment 4. That's where the concentration is higher than experiment 3, and that's also where the rate is higher. All right, so it's going to be experiment 4 numbers over experiment 3 numbers. All right, so now let's go ahead and plug in. So we have 6.9 over 3.45 equals, and then the concentrations were 0.0404 divided by 0.0202 raised to the y. Now, at this point, we're going to solve for y. So let's go ahead and divide that out. If we divide it out, we get 2 equals, and if you divide this, 2 to the y. So let me rewrite it over here. So this is a case where, yeah, we could go through like we did a minute ago. We could take the logs of both sides, but you could probably do it in your head, right? That's not too bad. 2 to the what equals 2. 2 to the what equals 2. I think it's 1. 2 to the 1 equals 2. So that means our exponent in our rate law is 1. So in other words, this thing is first order. All right, so first order with respect to y. So as far as that goes, if you don't like doing it in your head, you can always do the log way. You'll get the same answer. Okay, so now we're in pretty good shape. So what we found is both of our exponents. So we know that when we change the concentration of ammonium, whatever the concentration is, if we raise it to the half power, that's going to tell me what happens to the rate. And then y is to the first power, is a 1 in other words. All right, so we only got one more thing to do, and that's to figure out the value of K. We're going to do that on our next slide. Okay, so what have we left to do? So the one thing we haven't done is figure out the rate constant. The rate constant is K in that equation. So we're going to go ahead and look at the equation we've come up with. Let's make sure we remember what it was. It was rate equals K times the concentration of ammonium. And what was it to? Oh, it was to the half power, I think. Times the concentration of nitrite. And what was that one to? I think that one was to the first power. So we know those exponents now, but we don't know what K is. So we're going to do a little math. We're going to plug in our values, and you can use any experiment you want, the numbers from experiment 1 or 2 or 3 or 4. Plug in the numbers they gave you and solve for K. So just because it's at the top, I might as well. I'm going to go with the experiment number 1 numbers. So it says in there, let me rewrite it over here actually, rate equals K times the concentration of ammonium to the half power times the concentration of nitrite to the first power. So let's go ahead and plug in our numbers. So rate, the value for rate, 10.8. Now, if you look at the top, it's actually 10.8 times 10 to the minus 7. And on the right-hand side, we get K, and then the concentration of NH4, which is 0.02. Now remember, that's to the half power times the concentration of NO2 to the first power. All right, so now I got to solve for K. So the way I'm going to do that is just move these guys from the left-hand side, the 0.02 and the 0.2 from the right-hand side, I should say, to the left-hand side. The way you get that done, you divide by them. And if I do that to the right, I got to do it to the left. All right, so why is that helpful? Because now over here, right, these guys cancel. And we're left with this. K, oops, let me go back to blue. K equals 10.8 times 10 to the minus 7 divided by 0.2 to the half power. So just so you remember, right, half power is like the square root. So if you're not sure how to do that in your calculator, you can ask me, I'll show you. And then divided by also 0.2. So if you work it out, oh, that's a 0 there. If you work that out, the answer should be K will equal 1.21 times 10 to the minus 5. So that's what that constant is. So we can figure out the speed of the reaction by plugging that in, and and now we have our total rate law. Now the only one thing we haven't done is to find the units on K. So the way we're going to figure out the units again is I tend to just kind of think about it, but again, you can work through it a little more mathematically if you want. So for the units, I know that on the right-hand side of the equation, let me rewrite it. Maybe I should rewrite it. Rate equals K times the amount of ammonium to the half power and nitrite to the first power. So I know that rate is in molarity per second. I know this is like a half of a molarity. And then I know this is like 1 molarity. So if you put it all together, what I'm left with is molarity per second equals, well, I have molarity to the 3/2. So what do I need to stick here to make this work out? Well, if you look on the right-hand side, I basically have an extra half molarity. So how do you get rid of that? The way you get rid of that is you would take away a half. That would leave you with 1 left. That's what you want. So as far as the way I can figure that out, that tells me that what I am missing is I need to get rid of a half of a molarity. So it would be molarity to the half. And I also, when I'm done, I need a seconds on the bottom. So S would also go on the bottom. So the units would have to be 1 over molarity to the half and seconds. So let's just double check. Does that work? I'm going to finish it up right here. So let's see. Well, I'll have to do it down in this corner actually. So I need molarity per second. So if I have molarity to the half power and seconds on the bottom, and then that's times the molarity to the 3/2 that I ended up with for all those concentrations, that works. So my seconds would stick around. The 3.5, and you're dividing, so you subtract a half. That leaves you 1 left over, and that matches. So the units on K would be 1 over molarity to the half power in seconds. All right, so hopefully that helps you out. That can be a little confusing, but once you get the hang of it, hopefully it won't be too bad.